All right. Let's finish this thing up. Any questions or comments? So there's still some promise, but we are not done. I think the best part is still yet to come. Any questions? So this is the ground state or vacuum, I said. And now we can find the corresponding energy because the definition is A minus heating on psi 0. So that was our requirement to make sense of things. Then we can just consider, if I know the action of this, I can also look at the action of Hamiltonian. H psi 0 is h bar omega A plus A minus plus a half psi 0. And I can see this psi minus going and hitting this is going to kill this term immediately. Right? I can get rid of that. And that means this is equal to h bar omega over 2 psi 0. That means the corresponding energy E0 is equal to h bar omega over 2. Good. And now the problem is solved. For example, I can think about any other state. Because I know if I hit this state n times, energy is going to increase h bar omega times n times. Then a state like this, psi n of x, there will be some normalization constant. Let's keep it unspecified for a moment. We'll calculate it in a little bit. So A plus should act n times on psi 0. Right? And the corresponding energy is going to be En h bar omega n plus a half. Why? Yes, because we saw that right earlier. Every time you hit a given state, it increases. 1 time, 2 time, 3 time, I can enumerate the states like that. Good. And here, this is also a convention. In the particle in a box, we started from n is equal to 1, 2, 3, 4. Here we start from 0, 1, 2. That was our choice. Okay. Good. Therefore, we know the following. So H times psi n is h bar omega n plus a half times psi n. But I know what H is. H is h bar omega A plus A minus plus a half. So I can cancel these, and I can also cancel 1/2, and I can conclude A plus A minus psi n is equal to n psi n. And similarly, using commutation, that you can just replace things. A minus A plus psi n is n plus a half, n plus psi n. Good. So these are also nice, useful relations. Good. Any questions? Another thing to calculate is, so A plus hitting on psi n, we know it is going to be something psi n plus 1, right? Because it increases the energy. And because normalization, we still didn't fix it, let's call this Cn. And similarly, A minus psi n, I know this is going to be something proportional to psi n minus 1. And for normalization, let's use another constant Dn. Cn and Dn is the coefficients we want to find. Let's find, right? That's what I want to spend just a couple of minutes. First, like a note. Let me introduce a terminology and then use that terminology to find C and D. Yes, it would be nonsense. That's why if it is like A minus psi 0, if you want, I define it to be 0 separately. There is no psi minus 1. That's absolutely correct. Good?
Did you say end state or end state?
What's the difference?
End state or end in third or
End state here. So this is, I'm not sure what I said.
You said how many states are there for when you say end. You determine the order when you say psi n.
Like when I say psi n, it is end state, yes. But it's the state starts from zeros. There's like 0th state, first state, second state, and end state. So I want to consider something like this. Suppose I want to calculate, so this is dx, some f star, and let me do this for a plus, and you can do exactly the same thing for a minus and g. There's some function g, right, unspecified. They depend on x, but I'm not going to write to prevent cluttering. So this is also another function. There's like complex conjugation. And now let me unpack. So this thing is equal to minus infinity plus infinity dx. This is f star. A plus was 1 over 2 h bar m omega. This is minus ip plus m omega x g. Good. So let me also write what P is. P is minus I h bar d dx. And if I multiply with minus IP, this is going to be minus minus plus, I square is minus. This is going to be minus I h bar d dx. Then I can also write it here, minus h bar d dx. So I'll play with this a little bit. I'll show you a relation that will be useful in a little bit. So let me write this in two pieces. In the first piece, I want to keep this, and in the second piece, I want to keep this. Okay, and now this is plus. Can you say in English, please? So here. So yeah, I think let's check. I always mess up with these things. So this is minus IP, and minus IP is minus I h bar d dx, minus minus plus, but I square is minus, so this is minus. So this is minus h bar d dx. So here, okay, I also want to take this convenience factor to front, right? Let's not worry about this. I can, because this is just a constant, they just move around. So this is equal to this term plus this term. Now at the moment, this is the nice thing. Okay, let's write it compactly if this annoys you. So this is like that. This is like that. Now, this x is like a number, right? But we said this is like an operator, but it's like a nice operator. So we don't have to worry about too much about this x. And at the moment, this operator, even though it is a number, it is in a form that looks like it's acting on G. But I can move it around, right? I can take it from here and put it in front of F, so it looks like it is acting on F. Good? So what I will do is I'll take this from here and put it with the conjugation here, m omega x. M omega x. Good? And this is like a real conjugation, doesn't change anything. Good? And here, I'm not as lucky, right? In this case, this is like a derivative acting on this. And I cannot just take it from here and put it there. What I need to do is, I need to do by parts. But now we know that u dv, v du, by parts is like not a big deal. I can take it from here and put it on F. Let's do that. So this is h bar d dx. And because of by parts, there will be any additional minus sign. This minus sign is going to be plus. And now this derivative is acting on F. Like this. Good? So let's go back. At the moment, it is like acting on G. And I can do by parts. And in the by parts, there is like a boundary term. But boundary terms are always 0 because these are nice functions. And the other one is going to bring an additional minus. And that additional minus is going to make this plus. At the end, this is going to be h bar d dx. And I can now take the derivative on f function and not on g function. Good? And now I want to write this h bar in a form. So this is that is like p. So I'm going to put it like minus I and times I. Nothing changed. Good. And now minus I h bar d dx is p. I'll erase it and write p. So this is p. And now I can bring this m omega factor here too. So this is plus m omega x. And this entire thing, okay, let me be very explicit with the parentheses. So this entire thing is acting on F, and there is complex conjugation. Now, since I wrote this piece, I can also take it back. Good. But now I know what this is, right? This and this is equal to integral dx. This is a minus acting on F, complex conjugated, times G. Any questions? So let's look at it together. I started with A plus acting on G, and I ended up with A minus acting on F. So this is A minus. That's what we found, right? No, we started with A plus. We started with A plus, and it turned out to be A minus. And now is the terminology for any operator. Any operator, there are like some mathematical properties, blah, blah, blah. I really don't care for A. There exists always another operator, and we are going to put a mark on this operator because this operator is related to A, and this is the dagger operator that stick to my speaking I cannot get rid of. And the property of this is such that dx f a g is equal to dx a dagger f. Okay, there is f star here. This is star here, g. Okay, there is always an operator I can take from one place to another place, And there's the relationship between these two is like a dagger is called adjoint or Hermitian conjugate of A. Good. Let's pause if any objections or any questions. Now, what I wanted to do is like I wanted to find these coefficients, right? With this new technology, I can do that. Let's continue our main task. And what I will calculate is I want to look at this object. Minus infinity to plus infinity. Let me just make it full screen. So this is A plus psi n star. And this is A plus psi n dx. I want to calculate this object. And now with this new technology, I can take this A plus from here. By the way, okay. So with this new terminology, as an example, if you want, A minus is adjoint or Hermitian conjugate or Hermitian conjugate. Sometimes we write H dot C dot for Hermitian conjugate of A plus. Okay. Yes? No, these are operators. A minus, A pluses. This is probability, but inside integral, I started with there's like an operator, and this operator is defined with these like unspecified functions f and g, such that operation is performed not on g but on f.
Just the integral.
Yeah. This one?
A.
Yes. Let's also write that, right? We defined it here. So we defined it here. Let's also write this. This is, you are right. Let me write that from the, so this is going to be Cn squared, because you can see this is, we defined it Cn. And this is going to be psi n plus 1 star psi n. But this is normalized 1. So this entire object, whatever it is going to be Cn squared. Good. Now what I will do is with what we introduced, I'll take this A plus from here and put it here. Because A plus is Hermitian conjugate of A minus. By changing its role, I can change its place. So let's do this. So the rule now, since I know the rule, I don't have to go and do bypass and things, right? I already have like a systematic way of doing this. Just bring it here and put A minus, get rid of this, and done. No calculation needed. Good. Now A minus, A plus, when I see this, I'm happy because we already have like a very nice relation, right? A minus A plus is n plus 1. Then I can just write yes. So it was like this. Let's go back. It was like this. And the earlier exercise showed that you can take things from here and put there with the Hermitian conjugation. But Hermitian conjugate of A plus is A minus. If it was A minus here and I bring it here, also you can see order is important. I'm not putting it here. I'm putting it here. The beginning of this conjugated term. If I had A minus here, it would come here as A plus. And this thing, the thing I'm happy is this is n plus 1. That means this is equal to, and n plus 1 is a number, it can just come out of integral and everything else. N plus 1 minus infinity plus infinity psi n star psi n dx. But this is also normalized. 1. Then we found Cn square is equal to n plus a half. Cn is equal to root n plus 1. Good? Where? This one? So because here, this is our definition, right? We said when you act a plus on psi n, this is Cn times psi n plus 1. And there are two of these here. One this, another one this. Cn squared and psi n plus 1 squared. Okay. No, this is n plus 1. No, this is n. So you start with n. If you act with a plus, it's n plus. Right? This is some Cn psi n plus. This is also Cn, okay, conjugation, psi n plus. There is, yes, this one, yes. Is that what you mean? Oh, thank you. Absolutely. Good. Therefore, what we found is, let me see if I skip anything. Okay, I think you can also, okay, exercise, find dn similarly. No, it is not. Let me write the result and try to verify that. So a plus acting on psi n is going to give you n plus 1 psi n. That's why it's safe to not assume anything. It's like instinctively minus 1, you can, but you can never know, right? You should always verify. This is psi n. This is root n. Psi n minus 1. Okay, and these are the this is just like you have like a normalized state and you act on it and you get another normalized state, but overall factor. Good. I think there was one more question there. Oh, yes. Thank you. Yes, absolutely. Yes. Thank you. Now, let's generate a couple of states like this to see that in principle, all states are obtained and all solutions are found. So if we have n is equal to 0, a plus psi 0 is going to be equal to 0 plus 1 psi 1. And then psi 1 is equal to a plus psi 0. So that's the first one. If n is equal to 1, a plus psi 1 is equal to 1 plus 1 psi 2. And I have psi 2 is equal to a plus 1 over root 2 a plus psi 1. But psi 1 was written in terms of psi 2. It is going to be a plus squared divided by 2 psi 0. And you can keep doing this. For n state, psi n is going to be a plus to the power n root n factorial hitting on psi 0. And the corresponding energy, again, I remind you, we already found h bar omega n plus a half. Any questions? Yes. I mean, you can also start from n0 here, right? But it's going to be psi 0 is equal to psi 0. And psi 0 is given. And also you have to, right? That's also given. Like psi 0 is the starting state, which we solved. And everything else is built from psi 0. Okay, let me emphasize. The goal with all these details to expose you to terminology, jargon, and the techniques, right? All of these things, you can see exactly like a box. We obtain all the states and all the energies. Energies are discrete. As an exercise, if you want to find psi 1, psi 2, and if you have the epitide psi 3, and they are going to be like this. Here's so this is the ground state, is a Gaussian, and first excited state is like something like this, and the second excited state, okay, these are like tails going exponentially, and the third one is, right, ground state is even, first excited state is odd, second excited state is like even, ground state has no node, first excited state has one node, second excited state has like two nodes, and so on. Exactly like a box, they only have a little bit deformation. Let's also see if it is orthogonal exactly as in the box case. Let me also show this. And if you have appetite, I can show more stuff. If not, I can finish it there. Let's show orthogonality. So again, like this is a little bit experience. I want to try something. So this is psi m star. So this is a plus a minus psi n dx. And let's consider this object and let's see what this gives us. First, because of the relation here, okay, let me go back. I already showed you. A plus a minus gives n psi n, a minus a plus, n plus 1. Right? I know this. That's why whenever I see this one or this one, I'm happy. So this one is equal to, immediately, this is n, right? This thing acting on this is going to give n. And this is psi m star psi n dx. But what I can do is I can also hit on this side. Let's do it in two steps. This is equal to, so this is a plus, going here is a minus psi m star, and this is a minus, now hitting on psi n dx. And let me do one more step. Now I'll flip this guy. This is a minus, inside here a plus, a minus psi m star psi n dx. Whenever I see a plus a minus, I'm happy, but this time it is acting on m. So this is going to be m psi m star psi n. Now I compare this with this. Like if m is equal to n, no problem. This equation is perfectly fine. But if m is not equal to n, right? The only way these two equations can be equal is if psi m star psi n is 0. Is that clear? If m is not equal to n, the only way this equation can be true is if psi m star psi n is 0. And if m is equal to n, we already normalized. So let me just write it in compact form. So this is delta m n. And this is our normalization exactly as in the box. Good. And that means they are orthonormal, they are orthogonal to each other, and you can expand any other function in terms of these functions. Take any function which is well behaved, f of x, you can expand and now going from 0 to infinity, unlike the box. There are some cn's, and they are going to be psi n of x. Now these are more complicated functions that we have sketched here. Or if this is like an initial state, suppose this is like an initial state, psi of x 0. If you want to find time dependence, just take this form, write here t, and put here e to the minus I over h bar, en t. But unlike the box, here en is h bar omega n plus a half. Good. And the same story, nothing changes. Suppose somebody gave you this state and a measurement is made. Probability to get a state with n is equal to, I don't know, 5 is C1 squared. Subsequent measurements are 100% C1 and so on and so forth. Collapse and all these things we discussed at length. Any questions? How many people have enough for like one more calculation? Okay, so let's finish here, but then let me give this as a homework. Or if you want exercise. I think this is a problem 2.12. Find expectation value of x, expectation value of p, expectation value of x squared, expectation value of p squared, expectation value of t, and expectation value of v for harmonic oscillator at end state. Normally, I hate this kind of problem because you have to do a lot of integrals. But in this case, you are not supposed to do any integrals, right? The hint, write x and p in terms of a plus and a minus, and use the properties of a plus and a minus. And no integral is necessary. Okay? And if you don't know this and if you try to do integrals, it's going to turn into torture. But this is a good exercise for a plus and a minus. Good? Thank you.